Hello, Honors Chemistry, and welcome back to 7.8, where now we're going to talk specifically about the gas evolution reactions, right? So the essence is still the same, right? These are going to be aqueous phase reactions for the most part, right? At least one of the reactants will be. And these are also essentially the type of reaction where all we're going to do is switch the cation, right? And often what we're looking for is here we have an acid, right? And here we have a carbonate. Yes, in this case it's sodium carbonate, but it's a carbonate compound, right? We're going to expand our list of what type that other reactant needs to be in order to qualify as a gas evolution reaction, but we have an acid and a carbonate. But if we look at it again, it's still just a double displacement, right? We have two ionic compounds, so we're going to go ahead and find our cations, and we're going to switch our cations. That's really what's happening, yes? And so that sodium is now stuck to that nitrate, and that's where that product comes from. That hydrogen is now stuck to the carbonate, and that's where that product comes from. Now, in a gas evolution reaction, there is something special that happens, right? It turns out there is a set of compounds, right, that just instantaneously decompose, right? As in this will instantaneously decompose to form this, which means that when we do the reaction, what we're going to see is bubbles as the result of the decomposition of the H2CO3, where decomposition simply means the breaking down into smaller components, right? So if we take a look here, right, your book spells this out quite clearly, right, where we have an acid, right, and we have here in this case a bicarbonate, which also does this same process, right, and we switch our cations, right, and we end up with NaCl as one compound and H2CO3 as our other. But then this H2CO3, like we just talked about, decomposes into water and carbon dioxide gas, right? What compounds do you have to be aware of, right? So here we have our carbonates and bicarbonates, which we just talked about, and intermediate product is going to be the bicarbonate, and they're all going to form water, CO2, right, and a salt with the pieces that are left, okay? And again, that water and CO2 is the result of this carbonic acid breaking down, right? From another perspective, right, we have our sulfites and bisulfites, which do the same thing, right? We're going to form some H2SO3 as an intermediate, and that H2SO3, again, we're just going to break that down into water, and if we think about what that means, right, water is H2O. If I take H2O out of that H2SO3, all I have left is SO2. Yes, does that make sense? If I take out two hydrogens and an oxygen, SO2 is what remains, right? Which is then, if we look over here, we have H2O, SO2, and a salt, okay? Then we also have sulfides, right, which are a little bit more straightforward, right, where we produce hydrogen sulfide and a salt, right? And then finally, we have ammonium, right? And now ammonium is different because ammonium will react with a base. So it's base and ammonium. Whereas these three are acid reactions, yes? Acid plus that, right? So if we look here, we have acid, acid, acid. Ammonium, though, needs to react with a base, right? Because ammonium is actually acidic, which, again, beyond the scope of what we're talking about, right? To produce water, ammonia, right? Not to be confused with ammonium. Ammonia and a salt. All right, so let's just go ahead and do some reactions for practice, right? So it says that we're going to write the molecular and net ionic equations for aqueous hydrobromic and potassium sulfite, right? So hydrobromic, right? Hydro as a prefix tells us that this is a, right, binary acid composed of hydrogen and bromine. And we have potassium sulfite, right? So sulfite, so this is K2SO3, aqueous. Now, if we take a look at this, right, we're going to say, oh, well, we're just going to go ahead and switch our cations, right? Let's say that's the first thing that you feel moved to do, right? And I think that's a great thing, right? So we would have KBr, because K is +1, bromine is -1. There is water present, which means this is going to be aqueous because it's soluble. Potassium's group 1. Next up, we have H stuck to SO3. SO3 is a 2- ion, so this is going to be H2SO3, right? And then you might be like, oh, I don't know the state for that. Let's think. And then you would say, oh, that's right. H2SO3 is on this list of things that produce gases, yes? As in sulfites and bisulfites produce gases. So this compound is going to break down to form H2O and SO2. This will be our gas, and this will be a liquid, yes? So anytime we're tempted to write this as an intermediate, right, this is really going to just give us these two things, yes? And so our total reaction looks like this. And then if we were going to break this down into a so that's our complete molecular. If we wanted to break that down into a net ionic, again, we'd be looking for things that are ionic and aqueous, right? So we would have, let's balance this, right? So we need 2 of those, and we would have 2 of these, and then I think that's balanced. Okay, so we have 2H plus aqueous, and we have 2 bromides aqueous, and we have 2 potassiums aqueous, and we have SO3, 2 minus aqueous, and this is going to give us 2 K plus aqueous, 2 Br minus aqueous, water, not ionic, SO2, not ionic, okay? And we're going to go through and cross out the things that are exactly the same on both sides. So we've got potassiums are the same, bromides are the same. Everything else becomes our net ionic, yes? So then that last step was 2H plus aqueous plus SO3 2 minus aqueous is going to give us H2O liquid and SO2 gas. And that would be our net ionic. Yes, does that make sense? All right, and again, no worries, there will be plenty of practice. All right, thank you for listening, be good, and I will see you soon for redox.